The following has been developed by state and provincial agencies in association with the Agency for Instructional Technology. Together, serving education.
Hey, here are two on the solar system.
And one on the Milky Way.
Perfect. This oral report is going to be a snap, Jason.
An A for sure.
Okay, here's the average distance between the Earth and the Sun. 14,959,7906 kilometers.
What?
I'm not sure how to read it. What is this number anyway?
Beats me. Let's go to something else.
Venus is the planet closest to the Earth, a distance of 41,36,0000 kilometers.
What?
Maybe some other books are easier.
The numbers in here are even bigger. Listen to this one. Of the number of stars in the Milky Way, first there's the number 1, and then 1, 2, 3, 4. 11 zeros.
Impossible. This doesn't look like an A after all.
It's no wonder Heather and Jason are having problems. The kinds of numbers that they're wrestling with are much bigger than the numbers we usually run into. We are far more comfortable with numbers in the ones, tens, and hundreds positions. For example, 5 cupcakes, which is 5 times 1. Or 76 trombones, which is 7 times 10 plus 6 times 1. Or 253 pennies in a jar. That's 2 times 100 plus 5 times 10 plus 3 times 1. But how do we deal with the kinds of numbers that seem to go on and on and on and don't know where to stop?
This number is bigger than I am.
It makes my mouth go dry just to think of giving this report. I've got to get some water.
The nearest galaxy beyond the Milky Way is 1500.
Heather? Heather? Heather, wake up.
Where are we?
I don't know. I think we're lost in outer space.
Oh no. How are we going to get back to our space station?
Incoming information.
Instructions.
Thank goodness.
Your space station is located between the asteroid Ava and the planet Garvis. To reach it safely, you must set your controls exactly. Direction 1. Oh no, lots of big numbers.
They look just like the ones in the books.
If we do this wrong, we could be lost in space forever.
Hey, the numbers are arranged in groups of 3. I bet that means something.
Heather is onto something. The digits are in groups of 3, called periods, so we can read them more easily. There are groups or periods of ones, thousands, millions, and so on. Each period has 3 numbers, ones, tens, and hundreds. We've seen how it works for smaller numbers. Now let's see how it works for the thousands group or period. Whenever a number shows up here, we'll tack on the word thousand after it to show its value. For example, 47,000. And when the digit appears in the millions period, we add the word million to it. This number is 8 million.
Many years ago, there lived a very great emperor who had a huge army of several million soldiers. One day, the minister who was in charge of getting new clothes for the army gave the emperor a list of what was needed.
Some of the men need new caps. Quite a lot of them need new uniforms, and almost all of them need new boots. Give me the money, Your Highness, and I'll look after everything.
Oh, no. I don't trust you with so much money. I'll order the clothes myself.
The only trouble was, although the emperor was a great leader, he wasn't much good at reading big numbers.
Let me see. What's this? There's 100. There's a 5. So that must be 105 caps. And 674 uniforms. And 300... and 3,208 boots. Yes, that must be it. That's what I'll order.
But when the emperor inspected his troops in their new clothes, he had a nasty shock. Some of them had no caps, quite a lot of them had no uniforms, and almost none of them had any boots. So the emperor was obliged to ask the minister for help.
I didn't order enough clothes. I must have misread the numbers. What did I do wrong?
The secret of reading big numbers, Your Highness, is to separate them into groups of 3 called periods. You start on the right, 1, 2, 3. These are the ones or units, period. And then 1, 2, 3. These are the thousands. And 1, well, that's all we have. These are the millions. Now you go from left to right. How many millions? 3. How many thousands? None. How many ones? 208. Now you read the number. 3,208 boots. The same method applies to the smaller number of uniforms. In the thousands group, there are 60. In the ones group, there are 74. So that's 60,074 uniforms. And as for the number of caps, there is 1 in the thousands group and 5 in the ones group. That makes 1,005 caps.
So, to tackle a big number, you cut it down to size by separating it into groups called periods.
Let me give you 3 simple tips for conquering those jumbo-sized numbers. First, see how many groups of 3 digits, or periods, there are from right to left. Next, determine the name of the period farthest left. And finally, read the number by saying the number in each period and giving it the right name. Just for fun, let's try this system out on a few numbers from the Guinness Book of World Records. Now here's an impressive achievement. The record for the most jumps in pogo stick jumping. Let's see. We have 2 groups of digits. The group farthest to the left is in the thousands period. So we read the 3 digits in that group as 122 and tack on the word thousand. Then we move to the next group, which is 171. So the whole number is read as 122,171. Wow, that's a lot of times to bounce up and down. And here's one of my favorites. The largest number of teeth ever pulled by a single dentist. The number is tricky because of the zeros in the thousands period. But don't let that throw you. We just skip over it. The dentist pulled 2,744 teeth. Ouch! Well, as you can see, even jumbo-sized numbers can be tamed.
Okay, I think I've got it now. Prepare to set the distance control. 54,785,324 kilometers.
Got it.
Great. Next instruction. Set the compass for west, heading past the planet Garden. Now set the distance control for 3 million, this is hard, 2,050 kilometers.
You sure?
Yes, 3,002,050. Perfect. Okay, last instruction. Go due south over the North Pole of Garvis. 237,009 kilometers.
Done.
Now we can relax for a while.
If we haven't made any mistakes, that is.
We're looking here at signs that man has been very active in this area in the past, building a dam right across a nearby river. And we know exactly when the humans were here because they kept records. We know this was built 100 or 120 or so years ago. As a paleontologist, I deal with much larger numbers, though, much longer periods of time. We now believe the age of the Earth to be somewhere around 5 billion years. And there have been many plants and animals that were living here before man arrived on the scene. And as a paleontologist, I search for their remains, called fossils, and use them as clues to what the past was like. This is the tooth of a large white shark that was living in an ocean that was once very close to where we're standing. The ocean is gone today. The only way we know it was here is because of the rocks left behind and the fossils in those rocks. And if you get good dates on the rock material that this tooth was in, you'll find that this tooth is 50 to 60 million years old, which is a very, very long period of time, very large number. But not nearly now as long as another fossil that we find close by, the internal shell of a squid-like animal that was living here 65 to 80 million years ago. We sometimes call this an index fossil because this fossil lived only during a certain short period of time. It's like the index in a book. It tells you what page in the book of time to turn to when you see the fossil. Paleontologists deal with large numbers and long, long periods of time.
Look, there's the planet Garvis.
But I think we're flying too far north.
Incoming information.
Flight correction. Remove the digit 7 from the last distance given. You must subtract by the correct number and then travel southeast by this number of kilometers.
What does that mean? Get rid of the 7.
I know one thing. We can't just subtract 7. That wouldn't get rid of it.
And things are going so well.
How do you think Jason and Heather can get rid of the 7? I'll give you a hint. What's the place value of 7 in this number?
Place value of 7. Let's see. Ones, tens, hundreds. Look, Jason! The 7 is in the second period.
Right, that makes it 7,000.
So it's easy to get rid of it. All we have to do is subtract 7,000.
Right. We did it.
Incoming information.
Landing instructions.
Hooray!
Your final distance is 872 kilometers. For each kilometer, you will need 10 units of hydrogen and 1,000 units of helium. Please check now. Gee, how will we know if we got enough?
There's a simple way Heather and Jason can do this. Take a look at the place value chart. Remember, each time the number moves one place to the left, its value increases 10 times. 39, moved one place to the left, becomes 390. Jason and Heather can use this process to check their fuel.
I just thought of a way to do this. Let's see. Our last distance was 872 kilometers. And we need 10 units of hydrogen for each kilometer. So all we have to do is move the number one place to the left.
And I know how. I multiply by 10.
8,720 units. That's how many units of hydrogen we need.
That's just enough, if we're right about this.
Now the helium. Let's see. 1,000 units is 100 times 10 units.
So we should multiply 8,720 by 100. We need 872,000 units, and we have 2,005,808 units.
Way more than enough, if we're doing this right.
Hey, I have my calculator.
Great, let's double check.
Okay, the hydrogen is right. Right on the helium, too.
Jason, look up ahead. The space station. We're going to make it.
Heather, wake up.
Huh? Are we back at the space station yet? What?
MathWorks is a component of the Mathematics for the 80s project and is supported in part by Exxon Education Foundation. This program is produced by the South Carolina Educational Television Network under the supervision of the Agency for Instructional Technology.